Hello, good evening, everyone.
Good evening, sir.
Good evening. Ruth, are you there?
Yes, I can hear you.
Hello?
Good evening, sir.
All right. All right. Good evening. Mukhtar. Idris. Idris, are you there? Hello, Mukhtar. Okay. Donald, okay. Donald,
Yeah, good
good
afternoon.
evening. I want to say good evening and welcome to, okay, all right. So I welcome all of us to this semester's facilitation of CHM102 Introductory Organic Chemistry. I want to generally welcome you and tell you to feel free, feel at home, always make yourself available for interactions, and you will never regret having this contact. Chem 102 generally will involve hybridization, nature of organic compound, orbitals, nomenclature, that is naming. It will also involve functional group classifications, and then we'll now have a detailed study of alkane, alkene, and alkyne. I want you to be so free. Don't consider maybe you had a very bad background in chemistry in your secondary school, or you have left school for so many years and things like that. We'll try as much as possible while you read the material. From the course page and also attend class. So we are starting, like I said, we are looking at Chem 102 Introductory Organic Chemistry. Before I go into bonding as the course material requested, I want to first of all ask, what is organic chemistry? Does anybody have an idea of what organic chemistry is? Okay, Mukhtar, go on. Mukhtar, go on. Unmute yourself and talk. Click on mute, and so you can share what you understand. Okay, go on.
Organic chemistry is the study of any, I forget, I can't remember. I know the meaning, but the thing, I forget it on life.
Voila, you forget it. No problem. No problem. Donald, Olga, are you there? Okay, so without wasting time, organic chemistry simply is the study of the chemistry of carbon and its compound, with exception to the oxides of carbon, like you have carbonates, carbon 4 oxide, carbon 2 oxides. Those ones are not part of organic compound. So the study of organic compound is what is called organic chemistry. And then organic compounds include carbon and carbonates and the other oxides of carbon. Carbon compounds are very classical in their reactions and things like that, and that is why a specified course too large and voluminous called organic chemistry is dedicated to study the carbon compounds and their reactions, their applications, and the rest of it. So, if you look around you, if you are in a village or maybe in a city that has some green plants, you will observe that the plants have green colors, and these green colors are made of chlorophyll, which are organic compounds. And likewise, as you observe nature, you come to meet so many aspects of organic compounds. And these organic compounds also have been found applications in various areas of life, in pharmaceuticals, in agriculture, in so many places. And that is why it is quite an interesting aspect. So, having said that, let us quickly go into bonding. What is a bond? A bond is just that electrostatic force that holds two atoms together. Okay? A force, electrostatic force that holds two atoms together is called bond. So, and in every bond, there are two electrons. In every bond, there are two electrons. So, we have used this bond to classify compounds as inorganic compound or organic compound. In organic compound, we have covalent bond. In inorganic compound, we have ionic bond. In ionic bond, there is total loss of electron and total gain of electron. The atom that gains electron is now called your anion, while the atom that loses electron is called your cation. And that is why cations and anion with a negative charge. You can see what we have here. This is the cation, and then this is the anion. The cation lost the electron, and the anion gained the electron. That is by way of electron transfer. The electron is moving from one atom to the other. Like you have here, this is atom 1, let us say the cation in sodium chloride, which is sodium, and the one electron in the outermost shell of sodium is now donated to chlorine, and it adds to the 7 electron in the outermost shell of chlorine, leaving the outermost shell of sodium to be empty, and then making the outermost shell of chlorine to be achieve the octet state. And this is perfectly what happens in ionic compounds or inorganic compounds. There are total transfer of electrons from one atom to the other. So ionic bonds form from the electrostatic attraction between oppositely these two here, the attraction between these electrons here and then the positively charged gives what is called ionic bond. Now, atoms become ionic by losing or gaining electron. I have said that when they gain electron, they become anion. When they lose electron, they become cations. So in covalent compounds, the molecules are formed by sharing, right? So in covalent compounds, no particular atom takes the electron and no particular atom loses the electron. The two atoms come together, they donate their 2 electrons and they share it, such that the 2 atoms will achieve either the duplet states or the octet states together, the 2 of them. None will have a total loss of electron, while the other will have a total gain of electrons. Such doesn't happen in covalent compounds. And that is why naturally covalent compounds or covalent bonds are stronger bonds than ionic bond, because in covalent bond, the bond itself is a force of attraction. Okay, look at the covalent bond here. So you see in covalent bond here, there is a attraction. Remember here, the atom with labeled red, there are 7 electrons in the outermost shell, and then the atom labeled blue have also 7 electrons. These atoms are not stable, and so they won't achieve octet states. None can donate one electron and share it together. So you see the 2 electrons here, where the green arrow is pointed, will be shared equally by both atom A and atom B. And by that, atom A will achieve octet states, and then atom B will also achieve octet states. So, okay, before we go into that, so in covalent bonds or covalent compounds, the force of attraction is dual, because there will be interaction between the electron of this atom and then the nucleus of atom A, and then the electron in the outermost shell of atom A, and then the nucleus of atom B, and that forms the bond. Okay, so let's continue. There is another term we need to get familiar with, which is dissociation energy. And this is the amount of energy required to break a particular bond, and is usually expressed in kilojoule per mole. So if a molecule has 8 bonds, of course, there is no such molecule directly in organic compound because carbon is tetravalent. What do I mean by that? An atom is said to be tetravalent when it's with bond to give 4 different bonds. 4 electrons, they behave like a cation where they donate. It's difficult to donate 4 electrons, nor will they behave like an anion where they will receive. It is also difficult to receive a total 4 electrons for free. And so the bond in breaking in the energy in breaking any of those bonds is called dissociation energy. So in methane, to break methane, you have CH3H. So this energy is 427 kilojoule per mole. Then CH3, to break CH3 to CH2H, you have 460 kilojoule per mole. To break CH2 to CH and H, you have 435 kilojoule per mole. To break CH to C and H, you have 339 kilojoule per mole. Now, I want you to take a note of something. Even though the whole of these things are coming from methane, which is just one organic compound, you can see to break each bond, you have different type of energy involved. And that is what is called dissociation energy. And it's different from bond energy. Bond energy is usually an average value for a particular bond. So if you are going to talk of bond energy of methane, it's different from dissociation energy of methane, because dissociation energy of methane will involve 4 different energies, but bond energy of methane involves just one particular energy. So this is the process once more, giving us these values. So if we add them up together, we have 1652. If we divide 1652 by 4, we get 413. And 413 is what is called bond energy, while the other ones are the various dissociation energies. Now, like I said earlier, that in every covalent bond, there is an interaction between the electron of atom A and the nucleus of atom B, and then the electron of atom B and nucleus of atom A. And what we call bond length is the distance between the 2 nuclei. You can see it here. This is the nucleus of atom A, marked here, and then this is the nucleus of atom B, marked here. The distance between these 2 nuclei is called bond length. Now, there is another thing that we need to mention, which is called bond strength. The strength of a bond decreases with the increasing bond length. That is to say that if the bond length increases, the bond strength decreases. It is normal. It is normal because the more you separate the molecules, or rather the atoms, the lesser the force of attraction, and that is the strength of the bond. So if bond length increases, bond strength decreases. So bond length decreases with increase in multiplicity, and that is to say that methane or alkanes, the carbon-to-carbon bond of alkane, their bond length will be more than carbon-to-carbon bond of alkenes, and then that of alkene will be longer than that of alkyne. And that leads also to the strength. And that is why the bond strength of carbon to carbon is quite more smaller. Okay, so bond length increases with increasing size of the bonded atoms. Yes, because if the size increases, remember, if size increases, the distance between the nuclei and the outermost shell will also increase. And whatever is going to increase it will definitely increase bond length. And then there is something called the radius. If you look at these two atoms here, you see atom A from this middle to this length, to this point, and then from this to this point, you can see that of atom B is longer. And that is to say that the radius of atom B is longer than that of atom A. And so if anything will increase the size of atom A, invariably the bond length is going to increase. So these are the various bond lengths of molecules. Hydrogen is 74 picometer. Pico is times 10 to the power minus 12. And then ethane, you have this. Ethene, you have this. Ethane, you have this. And you can see that this is in agreement with this statement that the bond length decreases with multiplicity. Now, let us briefly look at factors affecting bond length. Number one is atomic size. I've said it earlier, the more the atomic size, the longer the bond length. Then electronegativity. Electronegativity decreases with increase in bond length. And it is normal because electronegativity is a function of how the bond, an atom will attract an electron. So if bond length increases, the strength of the nucleus will be reduced. And if the strength of the nucleus will be reduced, then the ability to attract an incoming electron will be reduced as well. The next one is bond order. PO is bond order, EN is electronegativity. So increase in bond length leads to decrease in bond order. Then the other one is percentage of S character. Increase in bond length leads to decrease in S character. And that is why, let us come back here. And that is why the S character here is quite more than this, and then this is more than this, because S character decreases as bond length increases. And you remember that C to C, and so it's going to have lesser S character, and then this will be having more S character than this, and so on. And I want to mention something so that when we go to study other things, we will also remember. Increase in S character leads to increase in acidity. Just take note of that. So bond angle. For a carbon to hydrogen or in alkanes, we have bond angle of 109.5. They are usually sp3 hybridized. Just hear it now. We are still going to go back to hybridization. And then for alkene, that is carbon to carbon double bond, their bond angle is 120 and their structure is trigonal planar, while the structure of alkanes are usually tetrahedral. And then for alkyne, they are usually linear. That's their structure, and their bond angle is 180 degrees, and then their hybridization state is sp. Structural formula. We have three main ways of writing the structural formula of every organic compound. Is either we use the Lewis structures. In the Lewis structure, you can see the carbon and the connections are well written out. So you see this is methane, carbon, H. That is a Lewis structure for methane. Then we also have the condensed structures. In the condensed structure, you can see we have just CH4. In condensed structure, you are not showing the bonding. The bonding are not shown, really. So you just show the atoms and their numbers. Then we also have what is called line structures or skeletal structure. In line structure, the atoms are not shown. You just use lines and then you get it. So this is methane, this is the condensed structure, then this is the line structure, because it's just one carbon. So we can't draw beyond one. So there is no way we are going to have another line structure for methane. But when we come to ethane, which is two carbon, you can see this is the Lewis structure, and then this is the condensed structure. Another way of writing condensed structure of methane is C2H6. They are still the same. Then this is the line structure where this point represents a CH3, and then this point represents another CH3. And then we move to propane, which is 1, 2, 3. This is the Lewis structure. And then this is the condensed structure. And then this is the line structure or skeletal structure. At this point, what we expect you to understand is just how a Lewis structure looks, how a condensed structure looks, and then how a skeletal or line structure looks. You may not be able to quite get what is a methane, ethane, propane, and the rest by now, because we have not actually started the study of alkanes. But then, suffice to note that at this structure, we'll be able to say, okay, this is the Lewis structure. Oh, this one is condensed, and then this one is skeletal or line structure. Having said that, let us quickly move to what is called orbital. An orbital is a mathematical expression or function that describes properties, characteristics of no more than 2 electrons in the vicinity of an atomic nucleus. It is a region of high probability of locating an electron. That's the simplest definition. So any region where there are high probability of locating or finding an electron, that is called an orbital. And going by the rules, Hund's rule and the rest, an orbital must contain maximum of 2 electrons. Okay, so that is why the first definition was trying to say properties, characteristics of no more than 2 electrons. So we have 4 different types of orbitals. The s orbitals. S orbitals do not have degenerate orbital. You must have known that from your inorganic chemistry. We have the p orbital. P orbital has 3 degenerate orbitals, and that is why p orbitals will contain 6, maximum of 6 electrons. Then we have the d orbitals. The d orbitals have 5 degenerate orbitals, and then that is why it can contain up to 10 electrons. The f orbital have 7 degenerate orbitals, and that is why it can contain 14 electrons. However, in the study of organic compound, carbon is the main thing we are looking at. And okay, we'll get back to that. And carbon has just 6 electrons. And if we do the electronic configuration of carbon, you will see that even the p orbitals of carbon are not filled. And so in organic compounds, we don't really bother ourselves with d and f orbitals, because organic compounds do not contain d and f orbitals, except substituents that are found in the molecule. So this is the structure of an s orbital. It is spherical, okay? And then this is the structure of a p orbital. Then let us quickly look at types of bond in organic compounds. We have 2 major types of bonds in organic compounds. One is sigma bond, and sigma bond is called single bond, is what you call single bond, which is formed by head-to-head overlap of orbitals. It could be head-to-head overlap of s to s, p to p, or s to p orbitals. So there could be an overlap of s to s orbitals. You can see it here. This is an overlap of s to s orbital, s here in blue, s, the second s here. Then sigma bond can also be formed from s to p orbitals. Okay, overlap of s to p orbitals. Here is half we have S, then this one here is p orbital. Remember the structure of p, which we saw here, you can see. Then we also have p to p, overlap of p to p orbitals. Now you can see both of them are p, both the blue and the yellow one are p. I want you to take note of how these bonds are formed. You can see the head on, the two heads come together, and that is why sigma bonds are said to be formed by head-to-head overlap. Now, the second bond type in organic compound is pi bond, and pi bonds are formed by sidewise overlap of p orbitals. Take notes, only side overlap of p orbitals gives pi bond, not s orbital, not s to p. Only p to p orbitals can give a pi bond. And you can see how it is formed. Look at this. You can see there is a sidewise overlap or parallel. Unlike what we have here, where it is this head that was overlapping with the head of an S or a P orbital. This is a typical organic compound which we have already seen before, which is methane. In methane, we have two different types of sigma bond. We have carbon to carbon sigma bond. This is carbon to carbon sigma bond. We also have carbon to hydrogen sigma bond. Hybridization. What is hybridization? Hybridization is simply the mixing of atomic orbitals to form new hybrid orbitals with different energies and shape than the component atomic orbitals. So actually what happens is that you have atomic orbitals of nearly the same image, and when they hybridize or when they mix, okay, we can use mixing, okay? When they mix together, you are going to get orbitals of equal energy. As a matter of fact, one of the main reasons of hybridization is to achieve orbitals of the same energy. Remember, before hybridization, these orbitals were not of the same energy, even though their energy difference weren't that much. But after hybridization, you achieve orbitals of the same energy. So the orbitals which undergo hybridization should not be energetically much different. I just mentioned it. They can be different, but not too much. Then the number of orbitals, hybrid orbitals generated is always equal to the number of atomic orbitals combined. That is to say that if two atomic orbitals combine together or hybridizes, you are going to have two molecular orbitals. So if four atomic orbitals combine together or hybridizes, you are going to have four molecular orbitals. Okay? Then the orbitals include the sp3 orbitals. These are the three major orbitals. The sp3 are found in alkanes and saturated compounds. sp2 are found in alkenes or wherever there is double bond. Then in sp, that is a triple bond, okay, alkynes, or wherever there is a triple bond. Take note that in every sp3 orbital, you have only the sigma orbitals. There was only a head-on overlap. While in sp2, you have a sigma bond, and then you also have a pi bond, one. Remember, you have double bond in sp2. So one of the bond is sigma, while the second one is pi. While in sp3, in sp, you have one sigma bond and two pi bonds. Remember, we also have agreed that each bond contains two electrons. Okay, so let us quickly look at electronic configuration of carbon. You can see, I already mentioned that carbon contains 6 electrons. So 1s will take 2, 2s will take 2, 2px. Remember, I also mentioned that p orbitals has 3 degenerate orbitals. So the px, py, and pz. So px takes 1, py takes 1. That is the ground state. Okay. So after hybridization, after mixing, you are now going to have sp3. In sp3, one electron of the 2s here is promoted to the pz orbital, so that we can now have 2s1, 2px1, 2py1, and 2pz1. You can see you have 1, 2, 3, 4. And that is why when molecules bond to compounds that atoms that are sp3 hybridized, they form single bond because there is no room for a double bond. So this is a 2s, this is 2px, this is 2py, and then this is 2pc. Okay, go back here. You see, this is the bond energy. Oh, sorry, bond angle of sp3 hybrid orbitals, 109.5. In sp2 hybridization, the 2s orbital is mixed with only 2 of the 3 available 2p orbitals. Usually, you have the 2px and 2py. So in sp2, one of the p does not hybridize. And that one that does not hybridize is the pz. Px and py will hybridize to form the bonds. And then the pz of one carbon will now undergo sidewise overlap with the pz of the second carbon. And this will now form a bond that looks like this, which is called a double bond. One of these is a sigma bond, the second one is a pi bond. And then the bond angle is 120 degrees. Then finally, among these hybridized orbitals, we have the sp. So in sp, the chemical bonding in compounds such as alkyne or nitrides, cyanides, they all have a sp hybridization. With triple bond is explained by sp hybridization. So in this molecule, 2s orbital is mixed with only one of the 3p, that is the px. So py and pz does not hybridize. And so px and py will now form sidewise overlap with the py and pz of the second carbon atom. So today, what we have done is to introduce you to the concept of bonds, where we mentioned that organic compounds have covalent bonds, while inorganic compound has ionic bond. In inorganic compounds, there is total loss of electron or gain of electron for a cation and ion respectively, while in covalent compounds, there is sharing, donate and share. The two atoms donate their electrons and they share to achieve octet states. And so we moved on to look at orbitals, we moved on to look at dissociation energy, okay? And then I was able to differentiate dissociation energy, which is with respect to a particular bond, breakage of a particular bond, from bond energy, which is an average of all the bond breaking energy required to break all the bonds. And then we moved to look at how you can get their bond energy, which and these various values are dissociation energies. And then we moved to look at the bond length between the two nuclei of the two interacting atoms. And then we mentioned that the radius, the radius is the distance between the nucleus and the outermost shell of each of these atoms. And that is why bond length is R1 plus R2. Somebody is asking which course is this. This is CHM102. CHM102, Introduction to Organic Chemistry. Okay. So we move on. And then we looked at the factors affecting bond length. We mentioned atomic size, which increases with increase in bond length. We mentioned electronegativity, which decreases with increase in bond length. We mentioned bond order, which decreases with increase in bond length. We also mentioned S character, percentage of S character, which decreases with increase in bond length. And then we moved to bond angle, where we looked at the various hybridization states, sp3, sp2, and sp. And the bond angle for sp3, 109.5 degrees, sp2, 120 degrees, sp, 180 degrees. And then this bond angle predicts the structure. So, and that is why tetrahedral, sp3 hybridized molecules are usually tetrahedral, whether than ethane, propane, butane, they are all tetrahedral molecules. And then we moved to 120 degrees for sp2, and these molecules are trigonal planar. Okay, this is what you find even in benzene and the rest of other compounds where you have carbon to carbon or carbon to oxygen double bond, or even carbon nitrogen double bond. It is not restricted to only carbon to carbon. And then we went further to look at the structural formulas, the Lewis structure. Lewis structure, or the condensed structure, and the skeletal or line structures. Then we moved to orbitals, which is the region with high probability of locating or finding an electron. And then we mentioned that we have 4 different types of orbitals in atoms, S, P, D, F, where S has just one degenerate, no degenerate orbital. P has 3 degenerate orbital and can contain 6 electrons. D has 5 degenerate orbital and can contain 10 electrons, 7 degenerate orbitals and can contain 14 electrons. You can see the structure of, but because organic compounds centers on carbon, which is just 6 electrons, so there is no point discussing D and F orbitals. S and P orbitals suffices to discuss carbon and this compound. And so this is the structure of S, spherical, and this is a dumbbell, P orbital. And then we move forward to look at the types of bond, the sigma bond formed by head-to-head or head-on overlap, and then the pi bond formed by sidewise overlap. However, in sigma bond, you can have S to S, P to P, or S to P, while in pi bond, you can only have P to P overlap. And then we move to hybridization, which I said is the mixing of atomic orbitals of nearly equal energy to get hybrid orbitals of equal energy. And it is additive, such that if you have 2 atomic orbitals and you mix them together or you hybridize them, those 2 atomic orbitals are going to give you 2 molecular orbitals. And then we move to look at the electronic configuration, the bond length, bond angle, and the structure of sp3 hybrid orbitals, sp2 hybrid orbitals, and sp hybrid orbitals. Okay, now let us interact. Somebody raised the question, and that person was asking if we should update it again. Okay, Idris, if you check even the mail I sent to you, facilitation, if you check the mail, you see that there was an attachment to that mail, and that attachment contained the PowerPoint for week 1. Okay, however, as it is a usual practice, this recording, because this is recorded, right? The recording will be uploaded in the course page, where you get the code with the passcode, with the link. You will be able to also go through the whole class. Okay, so and I expect that when you go through it, maybe in the next facilitation, you should be able to ask 1 or 2 questions where you are not where you were not able to pick accurately what was discussed. So there is already a room for all that you have said. So the PowerPoint has already been sent to your mail. However, the link to this class will be shared before the end of today, so that you can as well access it and get prepared for the next facilitation that comes by next Monday, 4 to 5 p.m. So please let us now discuss. From what I got from the course page, we are supposed to have around how many hundreds of people here? Unfortunately, I'm just having 14, 15 participants. Maybe others are not aware, or maybe they felt that we are not going to start today. I don't really know what their reason could be. Please, it is important to inform them that we have started, and we are not waiting for anybody. So what we are going to do now immediately is to take questions. Obeying, do you have questions? Although, let me not bite my tongue. Do you have question, Obeying? Okay, Gerald. Ata Gerald, are you there? Ata Gerald, are you there? Hello, Gerald. Danny. Okay, Umar. Who wants to talk? Please, if you are having network problem, nothing stops you from sending a question through the chat. You can say I've been responding going on. So if you are finding it difficult to contact, maybe you are having your network is not stable, you can quickly send a chat, ask your question via chat. We will read it out so that every other person can as well hear the question, then we will respond. Okay, Frank, you said you did not receive any email. Well, is it possible you submitted a wrong email to the university's account? Because the email I sent went directly to the email address which you used to register for this program, which has been provided on the course page. Okay? Which has been provided on the course page. So I don't know. Maybe you ask some other persons. Okay, let me drop my email address here so that you can quickly say hi, and then I will be able to get your email and forward the other thing to you. Okay, good. I'm getting your question. Let me quickly give Frank my email address. Frank, can you see the email address? So just quickly send me a mail so I can have your own email address, and I will send you the other thing. Okay, I'll take the question as they are coming. The first question here came from Ruth. Ruth is saying, I don't really understand the bond angle. Okay, what we have said under bond angle is that sp3 hybrid orbitals, or what you call saturated compounds, or what you call alkanes and other molecules that are having other carbon molecules that are having 4 bonds around, that these saturated molecules, the bond angle is 109.5. And this bond angle decides the structure. So once the bond angle is 109.5, obviously this compound is going to be tetrahedral, okay? Then for alkenes, or carbon to carbon double bond, or carbon to oxygen double bond, or carbon to nitrogen double bond, wherever you see double bond, carbon to anything double bond, there will be sp2 hybridization, and the bond angle is 120. And wherever you see this 120 degrees, it comes with a trigonal plane. The compound, the structure of the first one is sp hybridized orbital or carbon bond. These compounds are sp hybridized, and wherever you see them, their bond angle is 180. So they are linear. Okay, so the structure of the molecule will always be linear. So we have 3 main bond angles for the saturated, the double bond, and then the triple bond. 109.5, 120, and then 180. Okay, the other guy said, Idris says, sir, bond is the attractive forces between 2 atoms. What are the types of bonding? Okay, yes, it is an attractive force, but this attractive force is not usually the same. In ionic bond, which you see in inorganic compounds, there is total loss of electron from the cation to the anion, and that is why cations are positively charged, and then anions are negatively charged. However, in covalent compounds, as you found in organic compounds, there is no total transfer of electron. What you have is donating and sharing. Okay, the 2 electrons are shared by the 2 atoms. While in inorganic, one of the atom takes the 2 electrons, the anion, and then one of the atom loses totally the cation. And that is why the cationic property of an atom depends on its ability to lose electron. And so that is why members of group 1, okay, are usually much more reactive because they can easily lose their electron. Likewise, members of group 17, they are also usually more reactive because they only need 1 electron. However, in organic compounds or in covalent gain of electron, then Tertius asks, sir, I have a question. The available 2p orbital in sp that is mixed with the 2s orbital is 2px, right? Yes. While 2py and 2pz remains unhybridized. Yes. It is the 2py and 2pz of carbon 1 that overlaps with the 2py and 2pz of carbon 2 to form 2 extra bonds to give you a triple bond. So what you are asking, you are correct. Okay, Ruth is asking for further explanation on hybridization. Like I said earlier, hybridization is simply the mixing of orbitals of nearly the same energy to get orbitals of equal energy. And these orbitals of equal energy that comes after hybridization is called hybrid orbital. If you look at sp3, for instance, you can distinguish 2s from the p3s. But after hybridization, you have sp3. There are 4 different there are 4 orbitals of the same energy. So you cannot differentiate any of the sp3. And that is why you cannot say in methane that this one is CH, or this one is this particular. What you know is that there are 4 sp3 hybrid orbitals. So you started with orbitals of nearly, underline that word nearly, they are not equal. If they're already equal, then there is no point for hybridization, because the essence of hybridization is to mix the orbital and get orbital of equal image. And so it is necessary that their energy will be close so that hybridization can easily take place. Okay, let me take your other question. Okay, is that your last question? Any other question? Any other question or comment? Okay, Frank. Frank, please, your question. Frank, your question. Okay. Sent a message. No problem. If you have sent a message to my mail, I will access my mail after this facilitation, and I will definitely respond. Okay. Yes, Idris. Every Monday by 4 p.m., inshallah, I'll be here and we'll be able to chat. So I encourage you to download the course material from the course page. Is already there. Download the course material from the course page. Read ahead. Of course, that is what this program requires, so that you read ahead. Then when we come for facilitation, you will be able to ask questions on things that you didn't understand. Thank you, Frank. Any other question? Okay. Okay, that's wonderful. Nana said he or she understood everything. Okay, that's good. That's good. That's good. Oh, okay. Omar, thank you. Thank you. Okay, so in the absence of any other question, like I said, in the next 2 hours, you can check the course page where it is written live facilitation. If you go there, you will see the link. Click on the link. There will be a link and a password. Get the password or passcode. Use the passcode and access this facilitation. You will be able to hear and look at it over and over again. Thank you. As I expect you next week, please use your platform and inform others that we have started, and let them always come here and come here on time. Happy meeting you all. All right, see you by next week, God's grace. All right, bye.